Hello, my name is Abdelrahman and today I'll be explaining structural analysis. So let's first start with simple trusses. A truss is a structure composed of slender members joined together at their endpoints. Planar trusses are used to support roofs and bridges. Roof load is transmitted to the truss at joints by means of a series of purlins, as you can see in both of the examples I have provided on the right. Planar trusses. The analysis of the forces developed in the truss member is 2D. Similar to a roof truss, the bridge truss loading is also coplanar, which is also visually seen in the two examples I've shown of a roof truss and a bridge truss. Assumptions for design. All loadings are applied at the joint. Weight of the neglected. The members are joined together by smooth pins. Assume connections provided the center lines of the joining members are concurrent, as you can see also the two examples I provided. Simple trusses. Each truss member will act as a two-force member. The force will be directed along the axis of member. The force can be tension tending to elongate the member or compression tending to shorten the member, as you can see in the example. As in figure A, tension is pulling the beam outwards while compression is pushing the beam inwards. Simple truss. Form of a truss must be rigid to prevent collapse. The simplest form that is rigid or stable is a triangle. So the method of joints. For truss we need to know the force in each members. Forces in the members are internal forces. For external force members, equations of equilibrium can be applied. Force system acting at each joint is coplanar and concurrent. Sigma fx equals 0 and sigma fy equals 0 must be satisfied for equilibrium, as you can see in the example that I provided above of the free body diagram of the figure that is provided. So the method of joints. Procedure for analysis. Draw the free body diagram with at least one unknown and two unknown forces. Start at a joint having at least one known force and at most two unknown forces. Find the external reactions at the truss support. Determine the correct sense of the member. Orient the x and y axis. Apply sigma fx equals 0 and sigma fy equals 0. Use known force to analyze the unknown forces. So the other method is the method of sections, used to determine the loadings within a body. If a body is in equilibrium, any part of the body is in equilibrium. To find forces within members, an imaginary section is used to cut each member into two and expose each internal force as external, as provided in the example I provided. The method of sections. Consider the truss and section AA as shown. Member forces are equal and opposite to those acting on the other part. Newton's law. As you can see in the first figure on the left, there is a small squiggly blue line labeled as a lowercase letter a. This is used to split the model to make it easier to solve for the problem. So the procedure for analysis. Of course, the free body diagram. Decide the section of the truss. Determine the truss's external reaction. Use equilibrium equations to solve member forces at the cut section. Draw FBD of the section truss which has the least number of forces acting on it. Find the sense of an unknown member force, summed moments about a point. Find the third unknown force from moment equation. So let's take an example. Determine the force in each member of the trusses below and state if the members are in tension or in compression. This question will be kind of long as we need to find the force in each member. But as we said, there is no certain order but to find with the least unknown member. So let's start with joint D from the free body diagram in figure A. First, sigma fx. So FDE multiplied by 3 over 5 minus 600 equals 0. FDE is 1000 newtons or 1 kilonewton, as you can see from the free body diagram. Sigma Fy must equal 0. 1000 multiplied by 4 over 5 minus FDC equals 0. So FDC is equal 800 Newton, which is in tension, and the 1 kilonewton of Fx is in compression. Joint C from the free body diagram in figure B. Sigma Fx must equal 0. FCE minus 900, which is all the forces on the x-axis, is 900 newtons in compression. Sigma Fy must equal 0, so 800 minus FCB equals 0. FCB will be 800 newtons in tension. Joint E is the same as the last two joints. Sigma Fx must equal 0, so negative 900 cosine 36.87 degrees plus FEB sine 73.74 degrees equal 0, resulting in FEB equaling 750 newtons in tension. Sigma Fy for joint E, FEA minus 1000 minus 900 sine 36.87 minus 750 cosine 73.74 equals 0. FEA thus equals 1750 newtons or 1.75 kilonewtons in compression. Joint D, we have to find FDC, which is the sigma Fy. FDC sine 60 minus 8 equals 0. FDC equal 9.238 kilonewtons in tension or 5.24 kilonewtons. So sigma Fx FDE minus 9.238 cosine 60 equals 0. FDE equals 4.619 kilonewtons in compression or 4.62 kilonewtons in compression. Joint C, sigma Fy equals 0. FCE sine 60 minus 9.238 sine 60 equals 0, which results in FCE equaling 9.24 kilonewtons in compression. Fx equals 0, or the sigma Fx must equal 0. 2 multiplied by 9.238 cosine 60 degrees minus FCB equals 0. FCB thus equals 9.238 kilonewtons or 9.24 kilonewtons in tension. Joint B, sigma Fy equals 0. So FBE sine 60 minus FBA sine 60 equals 0. So FBE equal FBA, which equals the force, or they equal each other. So, or sorry, I apologize, Fx. Then we have to look for the Fx, sigma Fx, which equals 0, and it has one unknown. 9.238 minus 2 F cosine 60 degrees equals 0, which thus results in 9.238 kilonewtons. So FBE is 9.24 kilonewtons and FBA is 9.24 kilonewtons. Both equal each other, but one is compression and the other is tension. Joint E, sigma Fy equals 0. EY minus 2 multiplied by 9.238 sine 60 equals 0. EY then thus equals 16 kilonewtons. Sigma Fx equals 0. FEA plus 9.238 cosine 60 minus 9.238 cosine 60 minus 4.619 equals 0. FEA equals 4.62 kilonewtons in compression. As you can see, the question was very long as they were asking for each member. But some questions ask for specific members of, as you can see in front of us, it says determine the force in members CB, CI, EH of the truss shown and state if the members are in tension or in compression for the figure below. So this is a lot simpler because it's asking for specific members. So the support reaction, applying the moment equation of equilibrium applied about point A to the free body diagram of the truss. So the moment of point A equals 0. So 40 multiplied by 1.5 plus 30 multiplied by 3 plus 40 multiplied by 2 minus Fy multiplied by 4 equals 0. Fy equals 57.5 kilonewton. Sigma Fx equals 0. Ax minus 30 minus 40 equals 0. Thus results in Ax being 70 kilonewtons. Fy, sigma Fy equals 0. 57.5, which we got from the moment, minus 40 minus 50 plus Ay equals 0, resulting in Ay being 32.5 kilonewtons. The method of section using the left portion of the free body diagram, we have to find the sigma moment of point E, which is negative 57.2 multiplied by 2 plus FGH multiplied by 1.5 equals 0, resulting in FGH being 76.7 kilonewtons in tension. That's the first part of the answer. Moment of point H, negative 57.5 multiplied by 4 plus FED multiplied by 1.5 plus 40 multiplied by 2 equals 0. FED thus equals 100 kilonewtons in compression. To find the sigma Fy, 57.5 minus FEH, 3 over 5 minus 40 equals 0. FEH thus equals 29.2 kilonewtons in tension. These are the three answers, and you can see from the figure, from figure A we got the first part of the answer, and figure B we got the second part of the answer, thus resulting in finding the forces on each member, on the members provided. That's the end of our video. I hope you understood, and I hope there's no other questions, and structural analysis is a lot easier. Thank you very much.